Hello and good morning, everyone. Good morning, Professor Liu. Yeah.
Morning.
So today is the last day of our PhD school for lectures. So I just want to remind all of our attendees. So tomorrow morning at 8:30, we will have an international forum, also online. Yes, and we hope and all the attendees of the PhD school will join the international forum. We have a very some important keynote speech from the world leading scientists in the power electronics and the power systems, and join the discussions of the future energy systems with high proportion of power electronics. Hello, hi. I think today and who host the meeting? Yes, our TA, and please keep sharing the slides. Yes. Okay, sure. And please show the slides. So we just wait 1 minute. So I think the attendance and number is increasing. I think during this week and for the other lectures, and averagely we have the online leave. The attendance is around 100. Since we still have in the 2 on-site classroom, one in Chengdu and the other in the Tsinghua University. So in the totally the attendance leave is around and averagely 150, and but our total registrations is over 210. I think in some of the students, maybe because of the time difference, they cannot to take lectures online leave. But I think most of you can watch the playback. We have already recorded all the lectures, so and also send the links to all the attendees by email, so you can download and watch the playback. Okay, so good morning and good evening for everyone, and it's time to start our the lectures of our 2021 Asian PhD School on Advanced Power Electronics. So today, and it's our great honor to invite Professor Jinjun Liu to give the lectures on the recent advance in small signal modeling of power motors and distributed power systems. So at the beginnings, I would like to give a brief introduction to Professor Liu. So Professor Jinjun Liu is the distinguished professor of power electronics at Xi'an Jiaotong University and sponsored by the Chinese Changjiang Scholar Program of the Chinese Ministry of Education. And Professor Liu was the recipient of the Delta Scholar Award, the Changjiang Scholar Award, the Outstanding in the Scientific Worker of the Nation Award, and also he had received the IEEE Transaction on Power Electronics and for many times, prize paper award for many times. And currently, Professor Liu is the Vice President of IEEE Power Electronics Societies. Also, and he initiated these Asian PhD schools and hosted the first 2 rounds in the year 2019 and 2020, which is one in offline and online, the hybrid mode. So very, very successfully. So this year also Professor Liu and provide and very strong support to the Tsinghua, so we can host these in the Asian PhD schools. And also by now we have complete 8 lectures and all operate smoothly. So I would be very grateful to the support by Professor Jinjun Liu. Okay, so Professor Liu, and please start your lecture today. Thank you.
Thank you, Dr. Sun. I'm very glad that this year's Asian PhD School on Advanced Power Electronics has been going on very well so far. So let me first share my screen, right? That's the
yes. Okay. Right. Okay. So I think you can share. Yeah. Okay. Yes.
You can see my screen now, right?
Yes, sure. We can see, yes. And please show the slide, please. And yeah.
Okay. Let me let's see. In order to save some frequency bandwidth, let me also shut down my camera.
Yeah.
All right.
All right. It's fine. Yeah.
Okay. Good morning, good afternoon, and maybe good evening, everyone. I'm very glad to have the opportunity again to teach a lecture at the Asian PhD School this year. This year we have to go to a fully virtual form. So I see the program. It's a kind of very intensive program for this year's PhD school. Every day you have almost 6 to 7 hours lecture, 3 hours in the morning, 3 hours in the afternoon. It's very intensive. So in order to give you or give us all some time to rest a little bit, I'd like to separate my lecture in the morning part today to 3 parts. And after each part is kind of roughly 45 to 50 minutes. Then after each part, I'd like to have like around 5 minutes question and answers session. And then we take a 5 to 10 minutes break. Therefore, that means in the morning part today, we will have 2 times break. So therefore, you have some time to have some drinks or relax a little bit and not so feel not so intensive. That's my arrangement for this morning's the lecture. The title today is recent advances in small signal modeling of power converters and distributed power systems. I have been thinking about my lecture topic for this year. In the last 2 years, I was talking about the coordinating control of distributed power converters for microgrid. That was very well received in the last 2 years. But there is also a very important aspect with the issues related with microgrids or a power system with multiple power electrons converters, which is the small signal modeling. That has been becoming more and more important. I mean, in the beginning, I was only with single converters, but now it is more and more important with system level, with systems with multiple power electronic converters. And I feel that it is a good time to also let the young professionals in power electronics to know a little bit about the recent advances in the area of small signal modeling. So this year I changed my lecture topic from the coordinating control to the small signal modeling area. My lecture would be covering the 3 parts as shown on this slide. I will start from the developing trends and the challenges to the modeling of power electronic systems, especially the small signal modeling. And then I'll be focused on the recent advances, and in terms of the 3 specific aspects, including the modeling issues with a single converter level, and then at the distributed power system level, I will separate that part into the DC bus DPS system and also the 3-phase AC bus DPS system. And in the end, I would also like to talk a little bit about the future demand for the small signal modeling. Let's start from the developing trends. We start from the trends of the electric energy systems at all. I mean, as the whole electrical engineering area. I summarized the trends in my point of view into 6 aspects. There are many discussions about this different developing trends, but in my point of view, there are totally 6 developing trends in terms of the future of electric energy systems. The future electric energy systems will be more renewable in order to have less CO2 emission. It's going to be more DC to incorporate more DC bus in the system. It's going to be more mobile because more and more mobile devices or equipment or vehicles are adopting the fully electrified power system. And it's going to be more IT involved. Fundamentally, the future electrical energy system will be a cyber physical power system. And it's going to be more distributed generation and more electronic. Specifically, I would extend a little bit about the last 2 trends. Why in the future it's going to be more distributed generation? A basic reason is that in order to incorporate more and more renewable energies, and these renewable energies have to be not just in the in a more centralized form as we did before. They have to be more and more in the form of distributed generation. You have to have all the available renewable energy sources to have the ability to be connected to the whole to the general electric energy system. Therefore, these energy sources are all more and more distributed in the geographically and distributed. At the different connecting point of the whole electric grid. That's one reason. Another reason is that when you have all these generation sources distributed in the grid, then the supplying of energy to all the spread loads can be mostly done by the local generation, distributed generation. It does not have to, let me bring up the the pointer. It does not have to be transmitted for long distance from a centralized generation power plant through long distance transmission line to the final loads or users of this energy. It can be mostly supplied by the local energy sources. So therefore, it will save a lot of energy losses on the long distance transmission line. And the third reason that the future power system will be adopting more and more distributed generation is that when the local generation sources together with the local load and some energy storage components are integrated together to make a microgrid, then the reliability of the power supply will also be dramatically increased. And the reason is that when there is a failure in the large power system in the electric grid, and the local microgrid can be separated from the large grid, and therefore the local users can still be having access to energy sources locally. And when there is a failure in the local distributed energy sources, the local loads can still be reconnected with the larger grids together. Therefore, energy supplying will be coming from the larger grid. And in that sense, the higher reliability can be achieved. So based on that three reasons, I believe in the future, this trend of having more and more distributed generation will be very prominent in the future. The last trend I want to emphasize is that it's going to be more electronic. The fundamental reason of that is that in the beginning, this trend was started like many years ago for all these end users. When we adopt power electronic converters to process the electric energy that is supplying to the load, then the performance of the user and also the efficiency of energy utilization will be dramatically improved. The most dramatic example is in the area of motor drive. With motor drive power converters, all these motors will be having higher performance than before, much higher, and also the energy efficiency will be much highly improved. In recent years, this trend of adopting more and more electronic power converters has been extended to the area of generation areas, because in order to incorporate more and more renewable energies, all these renewable energies, they have to be interfaced to the grid or interfaced to the user through a power converter to transform the originally generated electricity to the form of voltage and current that can be accepted by the users or by the electric power system. And then if you look at the transmission level and distribution level of the whole electric energy systems, more and more power electronic converters are also adopted in order to improve the transmission and distribution performance. The fundamental reason behind this is that power electronic converters, they can control and process electric power precisely and fast with reasonable reliability and cost. In that sense, I believe in this future, more and more power electronic converters will be adopted in power system, and therefore in the future, power system will be a more electronic power system or electronified power system. So among these 6 trends that I've mentioned for energy system, I believe these two, the last two, more electronic and more distributed generation, are the 2 features that will bring revolutionary change to how the system is configured, organized, and operated. Under that background, there has been a lot of challenges to the small signal modeling of all these future electric energy systems in terms of both at the single converter level and also at distributed power system level. For single converter level, we need a better model to cover characteristics when the characteristics we're talking about, we care about, is more and more closer to switching frequency. Before, we have been only talking about the case when the characteristics we care about is very low, far away from the switching frequency. In that sense, the traditional small signal modeling has been good enough. Average model, which is the one that we have been using for many time, is good enough to cover that low frequency characteristics when that bandwidth of the system is much far away, much lower than the switching frequency. But in the future, when the in the cases when we need to look at the more and more higher bandwidth applications, the higher bandwidth might be very close to the switching frequency. In that case, we have challenges. The traditional average model approach cannot supply a good enough model for us. The other challenge at the single converter level is we need better model to cover the coupling among the three phases for three-phase AC to DC converters. There has been a lot of discussion about the small signal models for the three-phase AC to DC converters, but so far, most of the discussion has been just taken it for granted that we always believe that the model we're using is good enough. We never discuss how accurate the model we're using it is. For example, many people are still using linear model to simplify linear model, simplifying the three-phase circuits into single phase. And on the other cases, most of the people that are working in the area of small signal modeling for three-phase AC to DC converters are more likely to use the DQ frame small signal model or alpha beta frame small signal model. But what's the difference between the single phase linear model and the DQ frame small signal model and alpha beta frame small signal model? There is a lot of unanswered questions there. So we need to be very clear how to handle the coupling among the three phases for the three-phase AC to DC converter. The last challenge that I'm listing here is still we're looking for more user-friendly modeling process. That means we always want the practicing engineers would like to utilize the small signal modeling approach that we have developed so far. We want, in order to for all these practicing engineers to adopt that, these modeling processes should be simple and should be also very directive. It should be simple so that the engineers would like to use it. Every time when everything is very complicated, I don't think engineers would like to utilize that. It should be directive means it should be able to provide some insights or some ideas or directions for the engineers in terms of how I'm going to do the next round of analysis, or in terms of how I'm going to do the next round of design. How do I change my controller parameters? How do I adjust my parameters of the power stage? the modeling process should be supplying some directions in that sense in order to have a more user-friendly modeling process. At DPS level, there's also quite a lot of challenges based on the background that I've mentioned so far. The first challenge is that in the future, it could be a large number of converters involved in the system. And then these converters might have interactions with each other in the system, and how to handle this large number of converters interacting with each other in the system. Secondly, the structure and power flow of the system could be very complex. Okay, the structure of all these power converters in the system could be in simply PCC mode. Is the power, there is a common coupling point. There could be a mesh network form and structure where the power flow within the network will be very complex. And how do we handle that? And there is also another issue we have to consider in the case where there is communications among all these power electronic converters. That case will even more complicate the interactions among different converters. And therefore, that will make the modeling process even complicated. So these are the three challenges that I have seen so far for the system level small signal modeling. In the end, there's also a similar demand in terms of a more user-friendly modeling process. It needs to be simple, it needs to be directive, and there's also another need for the system level, which in which the modeling process needs to be scalable. Scalable means it should be very easily extended to cover larger number of power converters in the system. So based on that challenges, let me review a little bit what has been adopted or explored in recent years in terms of the small signal modeling, both at single converter level and system level, and see if we have good enough solutions to cover, to handle, to cope with those challenges so far. At single converter level, I would like to mention three things. One thing is the high frequency modeling of DC to DC converters under voltage mode control. I use the example the voltage mode control, but the idea actually can be extended to current mode control. And the second thing I would like to mention at this level is that the complex transfer functions, or in a more specific word, the complex coefficient transfer functions based analysis for AC to DC converters. And then third thing I want to mention is the decoupling control for AC to DC converters. And let's see these three examples specifically. First, starting from the high bandwidth or high frequency modeling for the DC to DC converters, we can start from a brief review about the traditional approach, modeling approach that we have adopted for many years, which is called arid model approach. And we take the example of buck converter as a basic DC to DC converter. Here is the whole picture of a buck converter under voltage mode control, power stage, both power stage and the control circuit. Here's the power stage where you have an input voltage source going through a switching network, and then this low pass filter on the load side, and you have the load on the right hand side. And in voltage mode control, we measure the actual output voltage compared with the reference voltage. That comparison is going through a compensator to generate a modulation waveform, or some other areas we call that as control voltage or modulation voltage. And that modulation voltage will be then sent to the PWM generator, which is usually, in this case, a comparator between the modulation waveform and the sawtooth waveform. And then that comparison is playing the function of PWM generator. And based on the output of that PWM generator, we decide on the turning on and turning off of the active switch within the switching network. That's the whole structure. Under constant frequency voltage mode control, this sawtooth ramp waveform is a constant frequency, and then the generated PWM waveform is also constant frequency. Only in the width of each PWM pulse within every switching cycle, that width could be modulated, and therefore the duty cycle of each active switch within each cycle could be modulated. When that is modulated, the output voltage will then be directly controlled. That's how we form the closed loop control on the output voltage. And then the blue curve, blue part of components I'm showing here is actually the case where when we discuss the loop gain of the system, where we apply a small signal perturbation at the modulation waveform here, and we see how that small signal modulation waveform would be affecting duty cycle, and then affecting the turning on, turning off of the active switch, and therefore affecting the output voltage. And the gain between the small signal perturbation and the output voltage is what we call the loop gain. And based on the discussion of loop gain, we are able to look at the overall performance, closed loop performance of the whole system, and we are able to look at how to design the controller or compensator for the voltage mode control. The traditional average model approach handles, let's see, the power stage with through the what we call moving average transformation. For every components, every signal in the circuit, we take the moving average transformations, and we're only looking at the moving average value of every signal. And then based on the relationship between among the moving average value of every signal, we are able to derive the here the relationship between let's see the every signal we want to look at. For example, here, if you look at the relationship between the duty cycle small signal changing to with the output voltage small signal changing, you have finally obtained this transfer function based on the average model. And therefore, in the if we also consider the loop gain, if we also consider the components in the control circuit, the overall loop gain would be this GD transfer function multiplied by the transfer function of the controller. Here it is. The overall transfer function would be a loop gain would be the duty cycle to output voltage transfer function multiplied by the controller transfer function, and then multiplied by the transfer function of the PWM generator. That's the overall loop gain, where FM is representing the model, the small signal model of PWM modulator. And in the traditional average model approach, we consider the, for example, here is the controller model, where typically if we take, let's say, place 2 poles at higher frequency place and 2 zeros at low frequency places around the resonant frequency of the power stage, one pole at origin. If we take that as the structure of the controller, then this is the overall transfer function of the controller. And for the PWM modulator, again, if we look at the small signal changing, let's see if we apply some changing in the modulator waveform. Let's see the change it from this black line to the red line, then the duty cycle will be also changed. And if you look at the relationship between the changing of the control voltage, VP wave, okay, and the actual duty cycle change, D wave, we have a relationship which is actually a proportional gain. Okay, so the PWM modulator in the traditional average model approach is considered as a constant gain component. That average model approach is very effective and quite accurate when the expected loop gain of the system is very low. When I'm saying very low, that means it is quite far away from the switching frequency. For example, if we are talking about the switching frequency at 50 kilohertz, on the left-hand side, and if we design the loop gain of the system to be 5 kilohertz, which is 1/10 of the switching frequency, then the average model approach actually can supply us with very good, a very accurate model. On the left-hand side, I'm showing in the red color, which is the loop gain that we can obtain through Saber simulation and through the what we call the frequency sweeping. Okay, let me go back to here. That means in the Saber simulation, we adopt a small signal sine wave source, voltage source here, applying that small signal perturbation signal to the control system, and then we measure how the output voltage will be responding to that perturbation, and we measure the relationship between the output voltage small signal changing and the small signal changing in the perturbation. Therefore, we actually can measure. We do frequency sweeping, and we can measure the loop gain Bode plot in terms of both magnitude and also phase angle. So the red line means the actual frequency sweeping results for the buck converter under voltage remote control in the Saber simulation. And then the green dashed line is the predicted average model approach based loop gain. Okay, you can see for most of the frequency range, in the case when we have the loop gain as 5 kilohertz, which is 1/10 of switching frequency, the frequency sweeping result is exactly matching with the average model approach predicted loop gain very well, until we come to the area when we look at the frequency, when we are looking at the frequency range very close to the switching frequency. here is the 50, I think this is 10 kilohertz, 20, 30, 40, 50 kilohertz. That's exactly where the switching frequency is. And around this area, you can see there is quite a large deficiency between the average model approach results and the frequency sweeping result. But in most of the cases, let's say below 20 kilohertz in these areas, they are matching with each other very well. But in the case when we're looking at the higher bandwidth design, for example, if we want to have the loop gain designed to be 20 kilohertz, okay, then you look at the frequency sweeping result by Saber simulation in the red line, and the green dash line by the average model prediction. You can see that the deficiency between the frequency sweeping and the average model results is getting very large. The deficiency will be extended not just above 20 kilohertz, but around 10 kilohertz. There's already quite big deficiency in the phase angle, and also if you look at carefully for low frequency in terms of the magnitude, the dashed green line actually has some deficiency at low frequency area with the red line. Okay, what is the reason behind that? That we cannot get accurate enough modeling based on the average model approach. There are actually two factors which are causing the deficiency when we look at the cases of higher bandwidth design. One is actually the switching ripple, because at the lower bandwidth, because the system bandwidth is designed at low frequency and far away from the switching frequency, therefore also it's going to be far away from the resonant frequency. Therefore, the resonant, both the switching frequency and resonant frequency components will be very small after the whole system. Therefore, the modulating signal over here, you don't see too much switching frequency ripple. Okay, at low bandwidth, you don't see very high switching frequency ripple. It's basically fully DC component or low frequency perturbation component. The switching frequency ripple does not show up here too much. But when you have a higher bandwidth design, when your system bandwidth is more closer to switching frequency, the attenuation of switching frequency ripple will be deteriorated. Okay, so therefore, larger and larger switching ripple component will be appearing at the input terminal of the PWM generator, and that switching ripple will have effect on the duty cycle, duty cycle generation through the PWM generator. If you look on the right-hand side, if that modulation signal is a pure DC signal, then the intersection point of that red line with the black line will be just this intersecting point. But when it contains switching ripple, that switching ripple will be changing that intersection point quite significantly. So that has that switching ripple at the modulating in the modulating signal will be having very dramatic effect on at the case when you have higher bandwidth. And the other case is the what we call as the sideband component effect. Because fundamentally, when we come to the PWM modulator, this PWM modulator is more like a the key component of changing time continuous signal to time discontinuous or time discrete signal. So here is the component where we change continuous signal to discrete signal. And therefore you can imagine naturally this PWM generator has the equivalent effect of sampling. Okay, has an equivalent sampling effect. When you are sampling a continuous signal and change it to discontinuous signal, you naturally have the similar in frequency domain. It is going to be a similar spectrum extension function. What we call spectrum extension function is that originally the continuous signal only, for example, if it contains only what we call a part, it covers only the part of the frequency range and contains this part of the frequency range, which is what we call as the main band or the major band of the signal. When it is going through this PWM modulator, the equivalent sampling effect will make this main band component extended to all these integer switching frequency places. So at the switching frequency, you have another band of components. You have 2 times of switching frequency, another band, 3 times switching frequency, another band. In the negative frequency range, it is also similar. Minus switching frequency, another band, and minus 2 switching frequency, another band. These are called sideband. And so these are what we call actually a spectrum extension effect in frequency domain caused by the equivalent sampling effect. When the bandwidth of the system is low, then all this sideband component at switching frequency, 2 times switching frequency, minus switching frequency, 2 times minus switching frequency, all these sideband components will be attenuated to very small value. So it does not affect this with this dominant band component. But when you go to higher bandwidth case, then this perturbation frequency might be even larger or very close to half switching frequency, which is over here. And therefore, this higher bandwidth of the system does not have a good attenuation of high frequency component. So at this half switching frequency area, you still have quite large, quite significant component. And therefore, for this sideband component, for example, at here, omega s sideband, you have when you have perturbation at omega p, then you at sideband you have a frequency component of omega s minus omega p. This omega s minus omega p will be at low frequency and even lower than sometimes even lower than half of the switching frequency, and therefore that sideband component would be very effective still within the bandwidth. It will be affecting the whole system. The traditional average model does not consider that sideband and only considers the main band. That's the other factor that would be affecting this issue. Okay, so 2 factors that would be causing the deficiency at higher bandwidth design. And this sideband components effect actually was firstly taken care of by people from Virginia Tech, and then they first reported this effect, and then they proposed a solution to handle that in about 15 years ago. Dr. Qiu Yang, he proposed that we need to consider, when we look at the higher bandwidth design, we need to consider this higher bandwidth sideband component. He the solution he proposed is that we need to at least look at, let's see, this what we call the side band at omega s, the component of omega s minus omega p, and also the negative frequency part, the other sideband component omega p minus omega p minus omega s, right? This component, or omega s minus omega p minus omega s. These are the sideband around omega s and the sideband around minus omega s. These are the most close sidebands we need to consider, including into our consideration. He proposed that we need to look at those components. Okay, and the solution he is proposing is that when we look at those sideband components, we would be able to, based on the waveform decomposition, for the p-dot modulator. Okay, when we adopt a small signal perturbation at the input of the p-dot modulator, and see how that small signal modeling, a small signal perturbation would be affecting the duty cycle using the waveform analysis, and find out the small signal changing in duty cycle. Okay, and in the duty cycle, we do the Fourier series extension to figure out how much sideband component it is. For example, when you apply a perturbation frequency at omega p at the input of p-dot modulator, we are through this process, waveform analysis, and finally the Fourier series extension, we are able to get, the sideband component at omega p minus omega s, how much component we'll be getting at the duty cycle side, how much component at omega p plus omega s at duty cycle side. Okay, so that's his proposed solution. So therefore, he proposed that because these two components, let's see, in the sideband, although we are looking at the sideband at omega s and minus omega s, actually both at these two sidebands, there is only one component which is very close, might be very dominant in the high band with design, which is omega s minus omega p, which is this component, and the negative frequency that is also that is omega p minus omega s. These two, actually the positive frequency component and negative frequency component, these are symmetrical. So this is the component we need to care about, because this is the lowest frequency component in the sideband component. So he proposed to, it is good enough to look at the frequency component at omega s minus omega p, or omega p minus omega s. Either way, it is okay. So therefore, the system we're looking at would be a system like this. Originally, we were only looking at, in the average model approach, we only look at the black line part. Okay, you have a reference over here. This is the feedback in from the output voltage, and then you go through the constant gain of the p-dot modulator. You go through the compensator, and then there is the this is the GD transfer function. That's the black line, the original average model approach. If we consider the sideband that is generated by the p-dot modulator at omega p minus omega s, then we know through the previous discussion, we know that this coefficient, how much sideband component will be generating. and that generated omega p minus omega s frequency component will go through, you can see that component will go through the power stage and then to the output voltage and controller and come back to the modulator again. So that frequency component at omega p minus omega s will be forming a closed loop itself, coming back to the PWM modulator. When it comes back to the PWM modulator, it will be going through the PWM modulator again. Therefore, in this case, it will be generating not only in the min band. In this case, the min band would be omega p minus omega s component. This itself will also generate a sideband component. That means omega p minus omega s will be extended to the frequency omega s. When it is extended back to the frequency omega s band, this omega p minus omega s will be plus the switching frequency omega s. When it is plus switching frequency omega s, it will be coming back to the omega p component. Okay, so therefore, if we consider that a sideband of the sideband component for the frequency omega p minus omega s, that sideband component will be coming back to omega p frequency. So therefore, this red line part is the part that is added to the original closed loop of the average model approach model when we consider the sideband component of omega p minus omega s. So therefore, this is going to be a better model for the whole system when we have a higher bandwidth design. And therefore, we are able to improve the overall closed loop model for the buck converter under voltage mode control by adding this red line part. So the overall loop gain, this is the original overall loop gain when we based on the average model approach, GD multiplied A multiplied by the constant gain of the PWM modulator. Now, the loop gain derived by the multi-frequency small signal model would be like this. It's going to be the original, let's see, the original loop gain developed based on the average model approach divided by 1 plus, still in the form of the original average model approach loop gain, but instead of substituting omega p into the perturbation frequency into the transfer function in the denominator, we're substituting omega p minus omega s here or here, omega p minus omega s into the loop gain substitution. With that, actually, that transfer function can be very well improved. Here is the example, still with the 50 kilohertz switching frequency on the left-hand side. When we are designing the loop gain bandwidth at 5 kilohertz, 1/10 of switching frequency, the simulation based on the based on the frequency sweeping is again showing in the red line. The blue dashed line is with the newly proposed multi-frequency model. You can see even for the high frequency part, when you look at the switching frequency range, they are matching with each other very well. With the case of higher bandwidth design, for example, 20 kilohertz designer, the high frequency part is also matching very well. So much better than the average model approach. But still, you can see this is not perfect. Okay, there are still 2 parts of deficiency. One part is over here at around half switching frequency to switching frequency area. The phase angle of the phase angle part, it has a very large deficiency. And even for the low frequency part, you can see there is a quite significant deficiency between the frequency sweeping result and also the multi-frequency result. And about a few years ago, there was one PhD student in my group. He proposed, he was very interested and look into this the issue and see how he can solve this part of deficiency problem. I think I would like to take a break here and see how new methods, new ideas were proposed to handle those part of deficiency that still exist with the multi-frequency small signal model proposed by Virginia Tech quite a few years ago. So let's take a break. Let's see, let's 5 minutes break, and let's come back around 10 5. Okay, 10:05. Let's come back. Take a break. Thank you. Okay, there was one question to show the page 13. Let me show you back. All right. So 10:05 already. Let's continue with the second class in the morning. During the break, there was one question in the chat box. It says, could we use a data-driven method for wide frequency modeling of power converters by ways of using large number of input and output data? My answer to that is, of course, we can. I mean, not just for the wide frequency or high bandwidth modeling. For any modeling, it could be used. I mean, it is a good idea. So the only flaws or drawbacks that I can see for the data-driven method are two sides. One side is that we need to take a lot of data. We need to have a lot of data. That means we need to do the measurement. Okay. For example, if you want to have the loop gain, accurate loop gain of a DC to DC converter, for example, buck converter under voltage mode control, then you put the buck converter under voltage mode control. You measure the loop gain of the system for many times and for many different combinations of parameters, including the power state parameters and also the control circuit parameters. And also you have to consider the parameters of the input. Okay, how much input voltage it is, how much load current it is, we're looking at, because for different input voltage and different load current, the loop gain might be different. So the first drawback is that we need to do numerous tests to get enough data. Okay, sometimes it's a very tremendous work we need to do. But of course, it's doable. I mean, for every kind of power converter under every single mode of control, we do numerous tests and measurement to get enough data. And then the other drawback I can see here is that, if you remember in the beginning, I mentioned the challenges to the modeling approach. One of them is that it's going to be it has to be user friendly. User friendly means there's one meaning in the user friendly item. It needs to be a directive. Directive means the modeling approach better can supply to the practicing engineers some insights, some ideas about how we can adjust our design and in which way, which component, which parameter would be the best parameters we are going to design and change. And should we change it to the larger direction or smaller direction? Things like that is what I call as directive. If you're talking about that, then the data-driven method does not supply enough directive enough results or suggestions to the practicing engineers. But it's doable. We can have some trying on the data-driven method on the modeling, okay, to see what we can do. Thank you for the question. Okay, let's continue with this modeling for the higher bandwidth buck converter under voltage mode control. As I mentioned, still there is deficiency between the predicted loop gain based on the multi-frequency small signal model and the measured, or what we call frequency sweep results. And then one of my students started work on this, and he figured out that there are two issues we need to take care in order to have an even better result. One issue is that when we consider the sideband components for different frequency range, we might want to actually look at different sideband components. Not necessarily always always the sideband at its switching frequency and minus switching frequency. He said for the frequency range between 0 and half switching frequency, for this frequency range, if you look at the sideband components, here is the picture. Okay, when you have a perturbation frequency below half switching frequency, then the sideband at switching frequency would be omega p plus omega s, okay, omega p minus omega s, okay, and then there's one additional sideband we need to take care, because other than these two components, which are very close to the bandwidth we're talking about, there's another component we need to take care, which is omega p minus 2 omega s. Okay, so therefore, but in the case when we're looking at when omega p is between 0 frequency to half switching frequency, omega p minus 2 omega s is a little bit too far away. Okay, it's over here, far away from the omega p, far away from the half switching frequency range. So when omega p is at this low frequency range, we probably don't have to consider that sideband component. We only need to consider omega p minus omega s and omega p plus omega s. But for the frequency range up to the higher frequency range, for example, between half switching frequency and switching frequency, in this frequency range, if you look at the frequency picture, spectrum picture, so let's say omega p is over here between half switching frequency and switching frequency. Then the you look at the sideband component, you figure out that omega p minus omega s is over here. Omega p plus omega s is over here. But then omega p minus 2 omega s is over here. So in this case, looks like the sideband component at omega p plus omega s would be between 1.5 omega s and 2 omega s. But the other component, omega p minus 2 omega s, would be between minus 1.5 omega s and minus omega s. This component, omega p minus 2 omega s, will be more closer to the bandwidth. On the contrary, the other component, omega p plus omega s, will be further away from the bandwidth. So in this case, for this frequency range between half switching frequency and switching frequency, the most dominant sideband component we need to take care would be omega p minus omega s, and omega p minus 2 omega s. Instead, at low frequency, the three components we need to take care is omega p minus omega s, and omega p plus omega s. So this student, actually Chen Xiangpeng, he proposed not to have the same sideband component for different frequency range. For different frequency range, we need to have different sideband components to be considered. Okay, so that's first idea he proposed. And the other idea is that he noticed that there is the influence of the ripple component, switching ripple component in the modulation waveform. Because when you are looking at higher bandwidths, this switching ripple will be quite significant, okay? And that will be affecting the PWM modulator, okay? It's clearly showing that if we only consider the DC component, and then that the intersection point between the modulating waveform and sawtooth waveform will be those points, okay? But when we consider the ripple component, the intersection point will be largely changed, okay? And therefore, when this intersection point will be largely changed, then duty cycle will also be largely changed. He said we need to take care of that. In terms of the ripples in the modulating waveform, there are two typical cases. Case one is that if you have good, very good design of filtering, this ripple originally in the form looks like a triangular waveform ripple in upper voltage. Through the filtering effect of the compensator, it will be becoming a sine wave or much smoother waveform at the input of the PWM modulator. And in other case, in other control method in the future, if you look to discuss about the kernel control, or you have a not so well designed controller, the ripple waveform at the PWM modulator input will still be having a not so smooth ripple, kind of still looking like triangular waveform. And therefore, the intersecting point of the modulation waveform with the triangular waveform, with the sawtooth waveform, kind of will be intersecting points that at this point, it does not have a derivable. I mean, if you look at the derivative of the modulating waveform at this point, it does not have a continuous derivative. Or in another word, the left-hand side derivative and the right-hand side derivative are totally different. So we have two different cases. One case is that we have derivable crossing point or intersecting point. And the other case is when we don't have a derivable intersecting point. We can discuss this into these two different situations. For the derivable crossing points is kind of simpler, because in this case, we can only consider the switching frequency. You can see how much switching frequency component sine wave will be obtained at the input of the PWM modulator. So in order to get how much switching frequency sine wave component is obtained at the input of PWM modulator, he proposed to use the generalized average model. Many people, many students, you probably know the generalized average model because the original average model approach, when we do the in that approach, we only look at the DC component or average component when we do the Fourier series extension of every signal in the system. For the generalized average model, is actually we're not only considering the DC component, we're also looking at the first order harmonic. Okay, so every signal in the original state space equation. Let's see, we have originally two state variables. One is inductor current, the other one is capacitor voltage. And we are able to write these two equations as a state space equation. In the average model, these two state variable IL and VC are replaced by their DC component of the Fourier series extension. But in average model approach, we need to not only consider the DC component, but also first harmonics at switching frequency. And we know the first harmonics for each state variable need to be always represented by two signals, actually two variables. Let's see if we see, therefore, each originally state variable will be represented in the generalized average model by three state variables. Okay, instead of having only one DC component, we need to have three variables: one to represent the DC component, two to represent the first harmonic component. For the inductor current, we need to do the similar thing. So the originally every state variable in the generalized model actually will be changed to three state variables. Okay, if you represent every state variable in three, in three state variables instead, the state equation that really we have two equations will be finally extended to 6 equations. Okay, and with 6 state variables, and then we can solve these equations at the steady state. That means when the left-hand side component are equal to 0, we solve this equation. We are able to get this at steady state how much DC component it is for every state variable for inductor current and also for capacitor voltage, and we are also able to solve this state equation to get the steady state how much first harmonic component it is in the power system. That means how much switching frequency component we have in the power stage. If you look back over here, when we have that's the first step. We are able to, using the generalized average model, to get how much component at switching frequency we will get at the input of the PWM modulator. Okay, to apply generalized average model to the power stage of the buck converter, and then going through. If we also consider that that component has been going through the controller, so you calculate for the controller how much gain we have, gain in terms of magnitude, in terms of phase angle, and you multiply that gain with the power stage gain, you get how much component you get at the PWM modulator input at the switching frequency component. So that's the first step. And the second step Chen Xiangpeng proposed is that he used this detailed magnitude and phase angle of the switching frequency ripple and do the waveform analysis for the PWM modulator. Again, similar approach that is adopted by Qiu Yang and many other researchers in this area. Adopt that waveform to the PWM modulator, and then adopt the a small signal perturbation at the input of PWM modulator, and see how that will be affecting the duty cycle waveform. And in the end, when you have the duty cycle waveform, you subtract by that from that the steady state duty cycle. Okay, substitute that by the steady state duty cycle, and then you get the small signal changing in duty cycle through the waveform analysis. And based on that, you can see the actually in the end, the small signal duty cycle will be affected by a factor of k. This k representing the effect of the ripple, how the switching frequency ripple would be affecting the system. You can see the switching frequency amplitude and switching frequency phase angle at the input side of the p-dialing modulator. That will be affecting this factor of k, and that will be affecting the gain of the overall p-dialing modulator. Okay, so therefore, when we consider the switching ripple, we can modify the originally multi-frequency small signal model. The original multi-frequency small signal model does not consider that. When we consider the switching ripple effect, that effect can be modeled as the modification on the gain for the whole system. Okay, and then we also propose to handle the sideband component differently for the low frequency range and high frequency range. Okay, for low frequency range, we look at the sideband of omega p minus omega s and omega p plus omega s. For high frequency range, we look at sideband of omega p minus omega s and omega p minus 2 omega s. Okay, and based on that two ideas, Cheng Xiangpeng proposed the final model for the whole buck converter under voltage mode control would be like this. So in addition to the original average model approach, which is shown in this black line part, and in addition to the red line part, we need to also utilizing the blue line part. And also we need to have a modification factor of k, to consider the switching ripple effect in the input of a p-dialing modulator. For the low frequency range, we are looking at the red line part, omega p minus omega s, and the blue line part, omega p plus omega s. And for the frequency range of half switching frequency up to switching frequency, we need to look at the omega p minus omega s and omega p minus 2 omega s. Okay, so that's the final model we propose. With that model, the final loop gain would be separated into these two parts, low frequency part and high frequency part. For low frequency part, this is going to be the loop gain of the system, and for high frequency part, this is going to be the loop gain of the system. And here's the example. I'm not getting into details. You can get into more details after class. Here's example for the actually the switching frequency of 280 kilohertz. But if we design the bandwidth to be around 120 kilohertz, how things will be different, how the model will be predicting the loop gain differently. And here is the let's see if we select the controller still as the two poles at high frequency, higher than bandwidth, two zeros lower than bandwidth, crossover frequency, and then one origin, one pole at origin. Then the overall transfer function, loop gain transfer function derived by the multi-frequency small signal model will be represented by this. But with the newly proposed which is proposed by Cheng Xiangpeng, and then these are the low frequency range loop gain transfer function. These are going to be the high frequency range transfer function. And then based on that, we can actually modify the design, closed loop design procedure, okay, to meet the final requirement. And here is the results. Let me show you. Let me go a little bit detail of this. Here is the comparison. Let me see. Okay, the red line is the measurement. Okay, the experimental measurement. The blue line is the newly proposed model. They can, when you have a bandwidth of 120 kilohertz, around 121 kilohertz, and around 80 kilohertz, you have a very close prediction of loop gain with the measured results. Much better, even much better than the generalized small signal model. Okay, this is the case for the voltage mode control. For the other case, on the voltage mode control, when you have a non-derivable crossing point or intersecting point, where the ripple voltage at the input of the modulating PWM modulator is not a smooth derivable waveform. Instead, it is a non-derivable point. The waveform analysis would be different. With that, we can also apply the similar idea. We still can do the waveform analysis. We also propose that in the end, in this case, the derived small signal model between the input of the modulation waveform and the duty cycle output, that should be represented by this equation. And in this equation, here S intersection point, or SMC, this is actually the average value of the left-hand side derivative and the right-hand side derivative of the modulating waveform. And based on that, we are able to again doing the waveform and get the how much how the ripple at the PWM modulator would be affecting the PWM modulator and affecting how much correction factor we would put in the overall small signal model of the system. Okay, I don't have the detail. I don't have time to go to the detail in the class. There is also papers published recently by our group. You can get into more detail after the class on that. And that actually also shows that this overall approach can be applied not only to voltage mode control and also to current mode control, where usually in current mode control, most cases, especially in peak current mode control, the intersection point between the modulating waveform and the PWM modulator are actually non-derivable. The other case I want to mention in the single converter level modeling is the complex transfer function method for three-phase AC to DC converter. If you remember, in the most of the cases, when we look at the transfer function of between the two, let's say two linear signal, okay, for linear system, let's see, when you have one input and one output, and then the transfer function of the system will be can be obtained based on the differential equation. And because this differential equation is a kind of all, in this case, the real coefficient differential equation. So the final transfer function we obtained all have a real coefficient. But theoretically, this input and output, both sides, doesn't have to be one-dimensional. It could be two-dimensional. So that means when you have two input variables and two output variables, the input variable could be represented by a vector or complex number. Output can also be represented by a vector or complex number. And then, therefore, the differential equations representing the relationship between input and output can also be represented by differential equations with complex coefficient. Okay, those coefficient in this case may not be real number. There could be complex number. Okay, and that's the what we call in this case, when you transfer that to a frequency range, then the transfer function will also be in the complex coefficient. Okay, so therefore, there is a possibility for a two-input, two-output system to be represented in the in frequency domain, not by originally most of our cases we're dealing with. In this case, when you have two input, two output, we were dealing with this model, a frequency domain model for the system as a 2x2 matrix. Okay, because we have to describe how each of the two inputs would be affecting each of the two outputs. So it's going to be a 2x2 matrix of real coefficient transfer functions. But if we represent the input by a vector and also output by a vector, and then the transfer function, there's a possibility the transfer function could be represented by a single transfer function, does not necessarily by a matrix of transfer function, but with a single transfer function, and this single transfer function actually will be having a complex coefficient. Okay, so that's the basic idea. So if you look at this, let's see, if you have two input for the system, two output also for the system, originally it is a 2x2 matrix. We can figure out that if this system transfer function is a symmetric matrix, okay, that means this let's say this 2x2 matrix has a other than these diagonal components h11 and h22, the anti-diagonal components elements, let's see, h21 and minus h12, if these are, let's see, h21, h12 are the same. Okay, let's see, then also these diagonal axes are the same. That means h11 is the same as h22, and anti-diagonal components are also the same if you do not consider this the sign. Okay, then this is going to be a symmetrical system, and the 2x2 matrix will be like this, can be represented like this. If this 2x2 matrix can be represented like this, then look at the relationship between the output and the input. Then the output actually can, if output and input, both output and input are represented by a vector, then this 2x2 matrix can also be simplified to be represented by a vector, where it could be simplified to be h1s plus j h2s. So therefore, the original, in this case, original 2x2 system, 2x2 matrix will be simplified to a scalar, one dimension transfer function. And only difference in this case is that in one dimensional transfer function has a complex coefficient. But what happens for asymmetrical system when the 2x2 matrix cannot be is not a symmetrical matrix? And further study shows that any asymmetrical system actually can be decomposed to two symmetrical systems where one symmetrical system has the original input. The other symmetrical system has a what we call conjugate input. Conjugate means the one dimension you have the same input, but the other dimension you have the reverse, exactly a reverse input. Okay, so therefore, any asymmetric system can be represented by two symmetrical systems that are taking two sets of conjugate input. Okay, and therefore, a system of what we call symmetrical AC/DC system converter system analysis method was developed. Okay, you can do small signal analysis and stability prediction for any symmetrical system in the three phases. Originally, for three phases system like this, we always try to do the coordinates transformation and change the three-phase system to be DQ frame or into alpha beta frame, or positive frequency, negative frequency, positive sequence, negative sequence frame. And therefore, the three-phase system actually are considered to be actually a two-dimensional system, two input and two output system. And then by taking the what we call complex coefficient transfer function method, these two input, two output system now can be modeled as a single input, single output system with the transfer function part of this system. Transfer function is actually not the traditional real coefficient transfer function. In this case, is actually a complex coefficient transfer function. This was actually very extensively explained in this paper published also a couple of years ago by Dr. Lena Hafner's. Okay, and based on that, we can use all the previously developed analysis method to do the analysis for the three-phase converters. And what we are trying to see as a third part of this single converter level modeling is that based on that approach of looking at the issues of this 2x2 system, a two input, two output system, using this complex coefficient transfer function, actually can also be giving us some more benefits. Okay, other than to do analysis in a one-dimensional coordinates frame, but also there are also other benefits we can obtain. Here is an example of one of my students that who were looking at the decoupling of the DQ frame or alpha beta frame control for the three-phase AC to DC converter. Based on the complex coefficient transfer function, he figured out that if you want to have the decoupling of these two channels, either DQ channel or alpha beta channel, for the whole system, whether these two channels are fully decoupled or not, or how much coupling there is between the two channels of the system, can be evaluated by looking at how symmetrical it is of the loop gain transfer functions for the system. For example, here is the complex coefficient transfer function of the system in either DQ frame or alpha beta frame or any other two-dimensional frame. He proved that whether these two-dimensional control channel are decoupled, fully decoupled, or how much coupling there is existing between these two channels can be checked by looking at how symmetrical it is for this complex coefficient transfer function. Symmetrical in the symmetricalness of the complex coefficient transfer function can be checked in this way. When I'm saying whether this is symmetrical, I mean when you look at the Bode plot of this complex coefficient transfer function, in the magnitude, it is symmetrical between positive frequency and negative frequency. Okay, in the magnitude, in terms of magnitude Bode plot. In terms of phase angle Bode plot, it is symmetrical. When we say symmetrical, it means the positive frequency part phase angle is exactly the reverse of our negative sign reversed of the negative part frequency. Okay, so this is what we call, as I'm showing here in this black dashed line, this is what we call exact symmetrical Bode plot in terms of magnitude and phase angle. So if the transfer function Bode plot of this 2x2 two input, two output system is like this, as I'm showing here in the black dashed line, then these two-dimensional control channels are fully decoupled. Okay, we can get very good performance for this fully decoupled control of these two channels. And if these are not symmetrical, then how much difference between the positive frequency part and negative frequency part will be showing how much coupling between the two channels. That's, I mean, this student, Zhou Sizhan, what he proved for the to evaluate the coupleness between these two channels, no matter in the DQ frame or alpha beta frame, or on any other two-dimensional frame. And based on that provement, he also proposed a new decoupling control. Okay, what he called as the reference current feed-forward control, and he compared the newly proposed control method with many other decoupling control methods by looking at the Bode plot of the complex coefficient transfer function, and based on that evaluation, he figured out that the newly proposed reference current feed-forward control actually has almost the best symmetrical characteristics in terms of the complex coefficient transfer function comparing to the other decoupling method. And on the right-hand side, he shows the decoupling control effect in time domain. You can see when you have a reference changing in the Q channel, but you don't have any reference changing in D channel. You want the actual output current in D channel and Q channel to follow that changing quickly and fast. With other decoupling method, there is always, I mean, this changing in Q channel will always have some effect on the influence on the D channel. Okay, most of the other decoupling approach, but in the newly proposed method, the changing in the Q channel reference does not really affect the D channel too much. Okay, that means the decoupling method of this method is very well realized. Okay, so that's the I think pretty much what I want to say for the single converter level modeling approach, especially the recent advances in that single converter level. One thing I was focused on was how do we handle the higher bandwidth modeling, and the other thing is actually regarding handling of three-phase converter, and in terms of how can we simplify the analysis. We can for symmetrical three-phase AC to DC converter, we actually can simplify that to a one-dimensional transfer function, and that one-dimensional transfer function actually has the merit of showing actually the how decoupled these two dimensional control channels are by looking at how symmetrical the complex coefficient transfer function multipole are looking like. I think with that, I would like to take the second break over here, and let's stop here, and let's come back at 11 o'clock. We will work on the second part on the modeling of distributed power systems. Of course, if you have any questions, you are very welcome to raise up. You can either put your questions in the chat box, or when we start the third part today, or you can also ask for in oral format. So let's take a break and come back at 11 o'clock. Thank you. Okay, let's continue with the last part for the today's morning lecture. During the break, there was a question raised up. Let me read the question. I have a question regarding the modeling methodology. He asked that we know the power electronic converters are inherently discrete systems. Will the build model inherently accurate if we directly model the converter in a discrete form? And how do we comment on the multi-frequency model and the discrete model? That's a very good question, actually. But there's one thing I may want to adjust your comment a little bit. Power converters are inherently, I would call that a mixed system. It's not discrete. It's a kind of a mixed system between discrete and continuous, time continuous system. And there has been two different areas or different approaches since the very beginning, many years ago, regarding the modeling of power electronic converters. One approach is more focused on the time discrete system approach, and the other is more on the continuous system approach. Even for the let's see, average model approach, and then what we have discussed today as the multi-frequency model approach, they are fundamentally looking at the time continuous system. Okay, for the discrete part, time discrete part, which is mainly the PWM modulator. Okay, PWM modulator is the time, the component that is changing time continuous system to time discrete system. And then after the PWM modulator, okay, at the power stage, the PWM modulator controls the active switch. And when active switch is operating, turn on, turn off, turn on, turn off, that turn on, turn off discrete time discrete option is actually smoothed by the power stage, okay, and transferred to time continuous system back, okay. So the time discrete part is only in the PWM modulator and the switch network within the power stage. And so far, I can see that these two approaches, they have their own benefits, okay, and own drawbacks, okay. But so far as I have been experiencing and what I have observed, most of the for most of the time, people still like to have a continuous time system point of view, because that is the part they are more familiar with. Okay, they are more familiar with all these control theories, feedback control theories, and all these methods that we can adopt for dealing with time continuous system, including transfer functions, including the frequency domain method, including the time domain method, including the Bode plot, and even for 2x2 system, you also have all this fully set of theory developed. how to do analysis and to do a controller design with the time continuous system. So in that sense, most of the practicing engineers, they still like using the continuous system oriented, even for digital control. Even for digital control, and then they still like to have what it is and understand what happens in the continuous time domain, and then adopt it into a digital control method. So so far in practicing, I think the time continuous approach is still what we have adopted, and in the practicing practice. Okay, I hope that answers your question. There's another comment. I cannot find a tutorial PDF today's program yesterday. Okay, so that's for the organizers. I think I have my lecture notes sent out yesterday. And in today's presentation, my lecture notes actually is a little bit different from the last version I supplied. I will supply also the real version, the actual presenting version later on to the organizer. So all the participants, you can download it from the website, my lecture notes today. Okay, so let's move on to the DPS part. I guess I should be a little bit faster for the rest part of the day's lecture. At a system level, one thing that makes the small signal analysis more complicated is that we are dealing with more and more distributed power converters. And why this is so difficult? Because for the conventional power system, where it's more centralized, okay, the small signal characteristics of the traditional power system will only be determined mostly by just a few very big generators. Okay, so if you want to find out the small signal dynamics of the system, as long as you are able to discuss just a very few big generators, it's enough, because all the other components are so small in power rating. So when you have a disturbance from this small loads or a small component, they really do not affect the dynamics, small signal dynamics of the whole system too much. The small signal dynamics of the whole system is only determined by just a few very large power rating generators. And in order to get the small signal dynamics of these few big generators, it is also not that difficult, because the dynamics of the generators are relatively slow and not so complicated. And also the parameters of the generator characteristics can be easily accessed either by their nameplate during the manufacturing process, or by doing some simple tests. But in the future, when we are dealing with power systems with more and more power converters and distributed generations, it's going to be totally different. In this case, the power rating of the source power converters and load components are comparable. Okay, the source power rating are not so good, not so big. Okay, energy sources coming from a distributed photovoltaic generator, wind generator, or batteries are not so big as compared to the load converters. So therefore, you need to consider the dynamics of, both the source converters and load converters. Okay, and the dynamics of the converters are usually much faster and more complicated than the synchronous generator. And the other bad thing is that these power converters are coming from different manufacturers, and they have different power state, different control methods. So therefore, their parameters inside converters are totally different. And usually the users of these converters, they do not know what parameters these power converters have adopted inside, and they're difficult to be accessed. And the most challenging thing is that in the future, there's going to be a great number of converters, and this number could be extremely high. So when we are dealing with dynamics, small signal dynamics of the system, we are dealing with a very big number of converters. So how can the traditional method be adopted to handle this? Okay, the traditional time domain state space approach may not be able to handle such a big number of power converters and such a big number of components that we need to handle their small signal dynamics. But it turns out that in this case, the approach based on impedance or terminal characteristics of a power converter would be a very effective approach. Basically because the impedance describes the terminal characteristics of power converters, which is a very good representation of possible interactions with outside circuit. So if this is a power converter, the impedance of this power converter really represents how this power converter would be interacting with outside circuit. Secondly, impedance can be measured through simple testing without any knowledge of power converter inner structure and parameters. You just can measure the impedance of the converter. And the total impedance, the other good thing is that the total impedance of multiple converters can be also easily calculated based on the measurement of each individual impedances. So once we know individual impedances of individual converter, then we are able to calculate based on this measured results the overall impedance of all these 2 or 3 or more converters when they are connected together. Thirdly, it is possible to draw analytical conclusions based on the impedance. We might be able to generate the final enclosed form, closed form or expression for maybe for the stability. For example, the stability margin, loop gain. We can also be all these parameters can be represented in the closed form expressions. So there is a possibility we can draw some analytical conclusions, and therefore we could come to a directive conclusion. Number 4, this impedance approach can also readily point to possible solutions when there is a stability problem happening by reshaping the impedance curve. If based on impedance approach, there is an instability issue happening, we can actually come to reshape the impedance curve to make the system stable. Many years ago in 1970s, there was the first impedance-based approach for stability checking proposed by Professor Middlebrook. This was called the impedance criterion, which says when you look at the small signal interactions between 2 submodules or 2 converters or 2 parts of the circuit system, where the energy is transferring from one converter to another converter or from one submodule to another submodule, the overall small signal stability of the system can be checked by treating the impedance ratio of the output impedance of the source converter and the input impedance of the load converter by treating that impedance ratio as the loop gain of the overall system. Basically, in the lower side picture, I'm showing that if I have a source converter input and output represented by this block diagram, and the load converter represented by another diagram, okay, each converter is actually modeled by a set of transfer functions representing relationship between the input side voltage and current and output side voltage and current. And therefore, when you connect these two converters together, source converter and load converter together, there is actually a additional closed loop set up in the system. You can see the output voltage of the source converter is also the output voltage, is also the input voltage of the load converter. Okay, and the output current of the source converter is also the input current of the load converter. And then through this red line here, okay, you can see we are actually forming an extra closed loop when you are connecting two converters together. And look at this extra closed loop. This extra closed loop gain is exactly the output impedance of the load converter, source converter, divided by the input impedance of the load converter. And therefore, based on the control theory, feedback control theory, we know the system, overall system stability can be checked based on this extra loop gain. And we call that, because very often call that as a minor loop gain, because in every converter, there is a major loop gain inside every converter. So this is what we call as a minor loop gain. Okay, this can be used to treat the small signal stability when you have two converters connected in a power cascaded manner. This can be explained by physical meaning that when you are connecting, let's say, one part of converter, if this part of converter is represented by a voltage source and some inner impedance over here, with another converter, and the other converter actually at steady state, if by look at the small signal, the other converter actually is actually looking like a equivalent negative resistor component. We know if this is the source converter module, and if the load converter is positive resistor, okay, then the whole system does not have any stability problem. But if this resistor is a negative resistance, very naturally, by physical meaning, that's a negative resistance, we will introduce a negative coefficient in the overall differential equation or in the transfer functions, because this is a second order system. We all know that. And the ordinary transfer function, when the load is a positive resistor, then everything is looking like this. But if the load is a negative resistor, then the coefficient of this second order transfer function might become negative, and therefore that might be causing the whole this second order system to be having a right hand side pole. Okay, and the right hand side pole will give you a instability issue happening. And you may ask, what happens? Why a load converter can be considered as a negative resistor? Let me put it in a simple way over here. When the load converter, let's say if there is a disturbance at the DC bus, and the DC bus has a increasing, changing. If this is a load converter, then this usually this load converter will be regulating. It has a closed loop control. It will be regulating the output voltage. So even when there is a increasing in the input voltage, the output voltage of the load converter would be maintained constant with closed loop feedback control. So therefore, when load output voltage is maintained constant, output power will be maintained constant. So power of at the output side of load converter will not change. So therefore, as the result at the input side, when you have input voltage increase, but the power transfer to the outside does not change, and if the within the load converter, there's no energy storage component inside load converter. At the input side, the energy that is taken by load converter will not be changed also, because no energy storage within load converter. So based on energy balance, input power will not be changed either. Okay. Again, if you think about this, the input voltage is increased, but input power does not change. That means input current will be decreased. So that means when you apply a positive small signal changing at the input voltage for the load converter, you have a negative input current response. Okay, so that means positive small signal changing, you have a negative small signal changing in current, or you have positive small signal in the voltage, you have a negative response in the small input small signal current. So that means in small signal sense, this load converter actually is a negative resistor. Okay, so that negative resistor will cause the overall system transfer function to be having negative coefficient. Okay, and therefore you have especially this item over here. So therefore you are dealing with a possibility that you have a right-hand side pole, a pair of right-hand side pole in the for the whole transfer function, and you might get into instability area. And then later on, people propose based on the impedance region that the concept of forbidden region. Forbidden region means if you want to ensure a system like this to be always in a stable area, then the minor loop gain of the system, that means the impedance ratio of the output impedance of source converter compared to the input impedance of the load converter, that impedance ratio should be always stay within the area, should not be entering into the forbidden region. And the first proposed forbidden region is actually this unit circle. Unit circle means within this unit circle, this is the area that this loop gain can be going to ensure the system stability. And the outside of the unit circle are all forbidden region that this minor loop gain should not be entering into. Okay, so based on that, you can develop the design requirement. Let's say once the source converter output impedance is known, you can design the load input impedance so that the impedance ratio or minor loop gain of the system does not enter into the forbidden region to ensure the system stability. Or in the reverse direction, if the load impedance is known, you can design the source output impedance again to ensure the impedance ratio to be within the unit circle and does not enter into the outside. Okay, that's the forbidden region area. And later on, because this is so forbidden region is such a big area, so this kind of forbidden region is really very conservative. Okay, you always stay in such a small area, and so there's a large area outside of the unit circle you cannot go. This is very conservative. So later on, some other forms of forbidden region are proposed, and which are much less conservative than the previously proposed forbidden region. For example, you propose this area to be forbidden region, you do not enter into, you still can, you have this side of very large area, this minor loop gain can go, but you still guarantee kind of the stability margin, like phase margin of 60 degrees and gain margin of 60 dB. Okay, we don't have detail time to get into detail of that, but that's the basic idea. you can do. Again, based on that, the newly proposed forbidden region, you can do the design of load impedance or source impedance with to ensure a certain stability margin in terms of small signal sense. But then there is one issue later on people figure out. When you adopt this impedance criteria, that criteria obviously is based on the power flow direction. If we follow that, okay, power flow direction, that means minor loop gain or the loop gain we are using to check the stability always is the source power converter output impedance compared with the load converter input impedance. If you always use that, in some cases, looks like it is wrong. For example, there has been reported results when you are dealing with, let's say, one case with the photovoltaic power converter or battery charging applications. There has been reported results that if we are still using the original impedance ratio as a source converter output impedance compared to the load converter, we will get wrong results. Okay, in that case, looks like the we use a reverse impedance ratio. In this case, for example, in the photovoltaic voltage, a photovoltaic converter connecting to the grid. In this case, looks like it is necessary to change that ratio to let's say the load converter, the load side impedance divided by the source side impedance. Okay, this has been reported in a few years ago, but people don't know why. And then one of my students, he came in and he said there must be something that is wrong with the original impedance criteria. He said the dynamics, the idea he was looking at is that if you think about this issue, the interactions between the source converter and load converter, he said that if the power stage of the converter, both source converter and load converter, if the power stage does not change, okay, both the components and the parameters not change, and control not change, no matter how the power flow direction it is, okay, whether it is flowing from left-hand side to the right-hand side, or from right-hand side to left-hand side, when the hardware and control method and control parameters are not changed at all, the small signal characteristics of both these two converters should not be changed. So therefore, the stability should not be changed. And fundamentally, the stability should not be dependent on how this power flow direction, what the power flow direction it is. Because there are characteristics, no matter in which direction power flow it is, their characteristics does not change. So therefore, fundamentally, he said, we fundamentally have to propose a criteria which is treating the stability issue not based on the power flow direction, but based on the terminal characteristics. And if you treat the terminal characteristics of a power converter, then there's only two types of characteristics we can consider. One is that if we consider the converter terminal as a voltage source or controlled voltage source, and the other one is that if we consider the terminal as a current source, or when you are trying to control the terminal current. Because in these two different cases, their characteristics are totally different. For voltage source control, you're always trying to control the terminal of this converter as a voltage source. Therefore, for this kind of converter, you can guarantee that when you apply some current disturbance at the terminal, you get voltage response. Okay, and then the system usually is designed to be very stable. Okay, but for this kind of converter, when you're trying to control the terminal voltage, you cannot guarantee the other case. That means the other case, when you are applying a voltage disturbance, you can get a stable current response. Okay, that part cannot be guaranteed. For the case when you are trying to control the terminal voltage, you cannot guarantee when you apply voltage disturbance, you get a stable voltage response. Okay, so for this type of converter, you can only guarantee the terminal impedance. That means you apply current disturbance, you get voltage response, and then the transfer function from current impedance, from current input from load current disturbance to the voltage response, that transfer function is stable. Okay, so we call this type of converter as, because the denominator is current, the upper side is what we call as the voltage. So voltage over current, that's the impedance. So we call this type of converter as impedance type or Z-type converter. For the other type of converter, when you are always, the control side is always trying to control the terminal current. For this kind of converter, we can always apply voltage disturbance to the terminal and get the stable current response at the terminal. So therefore, then for this type of converter, we are able to get always a stable transfer function from terminal current to terminal voltage, and that is admittance. So therefore, we call that type of converter that is trying to always controlling the terminal current as Y-type or admittance type of converter. And then we cannot apply we cannot be sure that when we apply current type of disturbance at the terminal, and we can get a stable voltage response, okay, for Y-type converter. So therefore, all the power converters are classified into these two types, Z-type and Y-type. For Z-type, we are able to describe the terminal characteristics of the converter by the impedance. It always has a stable impedance transfer function. That means the impedance does not have a right half plane pole. For the Y-type converter, which is very often you are trying to control the terminal current. For that type of converter, we always have a terminal admittance transfer function that we guarantee that admittance does not have right half plane pole, but we cannot guarantee that admittance does not have right half plane 0. Okay, so that's how we define the two types of power converter. Okay, and therefore these definitions of the two-type power converter do not depend on the power flow direction. No matter the terminal, I mean the power is flowing out of the terminal, flowing into the terminal of the converter, we always the terminal characteristics does not change. Okay, so we always have for this type converter to represent the terminal characteristics of the converter using impedance that has no right half plane pole, and we always can represent the Y-type converter by the admittance that does not have right half plane pole. Okay. You may ask a question, what happens if we are representing the Z-type converter with admittance, or Y-type converter with impedance? You might get into the case where you the Z-type converter Z-type converter admittance might have right half plane pole, okay, and Y-type converter impedance might have right half plane pole. Okay, that's the key issue there. So in other words, Z-type converter impedance does not have right half plane pole, but may have right half plane 0. Okay, so if we write the admittance of Z-type converter, that admittance might have right half plane pole. Okay. Similarly, for Y-type converter admittance does not have right half plane pole, but admittance might have right half plane 0. When a Y-type converter admittance has right half plane 0, then admittance has right half plane 0, then the impedance of Y-type converter will be having a right half plane pole. That will get the system more complicated. So therefore, based on that classification of two types of converter, again, we classify power converter into Y-type and Z-type. The actual stability criteria can be actually checked in this way. When you connect these two converters together, okay. Let's say if you have a Y-type converter connected with a Z-type converter, okay, no matter how the power is flowing, whether the power is flowing from Z-type to Y-type or flowing from Y-type to Z-type, doesn't matter. The stability of the whole system can then be checked by treating, you see, no matter the bus voltage or bus current can always be represented by a transfer function that has a denominator like 1 plus Z1 Y2. Z1, that means the impedance of Z-type converter. Y2 is admittance of Y-type converter. So that means we can treat the product of Z-type converter impedance and the Y-type converter admittance as the minor loop gain for the whole system, and does not depend on how the power flow direction is. Okay, so this was proposed a few years ago by one of my PhD students, Liu Fangcheng, and he proved that the stability criteria now has to be modified to look at by treating the source impedance, by treating the Z-type converter impedance multiplied by Y-type converter admittance as the minor loop gain. That actually is actually proved to be a more accurate criteria than original impedance criteria dependent on the power flow direction. There is a detailed verification through experiments and simulation about that. And then if you look at the connection of two converters, then there is a possibility of not only looking at the cascaded power converters where energy is flowing from one converter to another converter, but actually in the case when you have two converters connected in parallel, this parallel connection actually can also be treated. It's just like, okay, no matter how the power flow it is, I mean, in the traditional parallel concept we're dealing with, actually energy is transferring from the same direction, okay, both from converters to the load, or from both from the load to the converter. That's called parallel. But actually, that can be treated as what we call the generalized idea of a parallel connection. When you don't consider the power flow direction, basically, in the generalized parallel connection idea, no matter these converters are cascaded or parallel, that means no matter how power flow direction it is, whether it is flowing from one converter to another converter, or flow from both converters to the load, or from both from the source to the both converters, the interactions between these two converters are actually the same. They are interacting with each other through the small signal voltage and current on the terminal buses. Okay, so in this case, we should be classifying the connection not by power flow direction and classify the connection of two converters into cascade connection or parallel connection. We should treat all these connections in what we call as the generalized parallel connection, and classify the connection of two converters by the converter types of these two converters. And then in this case, there will be three possible connections among different types of power converters. One is what we have discussed, Z plus Y type. That means one converter is Z type, the other one is Y type. When you have both these two converters are Z type, this is what we call Z plus Z connection. And this is the traditional parallel connection. Okay, or both converters are Y type. This is what we call Y plus Y type connections. Okay, and for each of these three possible connection structure, we need to develop stability criteria. Okay, we have already done Z plus Y type, and then we should be able to done Z plus Z type and Y plus Y type. So therefore, we will be able to handle not just the traditional cascade connection of two power converters, we are also able to handle the parallel connection of two converters. We are able to handle the stability based on the relationship between their terminal characteristics, either in impedance representation or in admittance representation. I don't have time getting the detail of Z plus Z type of stability parallel subsystem for stability checking, but it can be obtained through this paper we published a few years ago. Also, the other type of connection, Y plus Y type connection, stability checking criteria can also be obtained based on a similar idea. Okay, so once you have the stability criteria for all different possible connections, Z plus Y type, Z plus Z type, and Y plus Y type connection of power converters, then we are able to handle the issue of dealing with a large number of power converters. When you are connecting not just two, but 3, 4, and more power converters together, no matter they are cascaded or parallel connection, or how many Z-type converter it is, how many Y-type Y-type converter it is, we can always propose a checking approach for the stability. One approach I can spend a little bit more time over here is that we can treat all the Z-type converter together as a overall equivalent Z-type, and we can treat all the Y-type converter together as an equivalent Y-type group. Okay, you have an equivalent Z-type group, you have an equivalent Y-type group, and for then you have to take two steps. One step is to check whether all these Z-type converter, when they connect together, are still stable. Okay, so you have to check the overall impedance, okay, of the Z-type group. Okay, once you know the individual Z of all these Z-type converter, you are able to check first the overall impedance of all the Z-type converter, and to check if they are stable, if it has a right half plane 0, based on the Nyquist criteria, based on that approach. And then you check that as a second step, you put the equivalent Z-type, equivalent Z module with the equivalent Y module. Okay, and then there's two possibilities. If there's no right-hand side pole, right half plane pole with the equivalent Z, then you just treat the overall system using this equivalent Z with equivalent Y to check the overall system stability. But there is also a possibility that this equivalent Z might have right half plane pole. Okay, in that case, then you need to check the stability based on how many right half plane poles you have in the overall equivalent ZEQ. Okay, so there is a detail about this stability checking criteria for multiple module power converter system. There's a detailed discussion you can get in the paper we have published before. I don't have time getting that into detail. There's also another possible stability criteria to treat every module the same. To treat every module as a Y-type converter, and then you can also get a stability criteria to treat the whole system stability. That has been already verified both using simulation and also experimental setup, and proved to be very accurate. Okay, I don't have time to go in detail. Let me quickly go to the last topic of this part, which is so far we are able to handle the stability checking issue for a system when you have multiple power converters, which is just based on the terminal for Z-type converter based on based on their impedance, for Y-type converter based on the admittance. So once you have each individual module terminal characteristics, we are able to check the whole system stability based on the proposed method. But then there is also final case when there is communications. Okay, when there's a communications between two modules, two converters, that will complicate the issue. That communication might change the terminal characteristics. Okay, so the terminal characteristics will be dependent in this case not just by the converter, each converter itself. It might be dependent on other converter, because the other converter will be affecting this converter based through control communications. That is a very serious problem. Many people have been working on this for many years, trying to model the interactions of two parallel converters when there is communications existing. But so far it's very difficult. Because the interactions through communication is even more complicated, very hard to model that. But then there is an idea came up also from one of my PhD students, Wang Hao. He said, can we model the communications interaction also again equivalently into the impedance of a converter, or terminal impedance or terminal admittance of a converter? And he really figured out a way to handle that. He said, when the power converter is under, let's say, under current sharing control, okay, then basically the power converter, this is the original power converter. When there is a current sharing control, then you had some additional control circuit over here. And usually the current sharing communications between converters are adopting different current sharing method. Let's say, for example, for master-slave current sharing method, you basically have a communication signal coming from the master converter. The master converter will be sending all the slave converter a reference signal, and that reference signal will be compared within each slave converter, with the actual current, of each master converter. If that slave converter current is different from the master slave current, and it will be adjusting the reference of the voltage reference of the master slave converter, so that it will be further adjusting. It will be further adjusting the inner the current, the voltage control and current control of this master slave module to adjust that each individual master slave module current to follow, in the end, to follow the actual master converter current reference. So in the end, when every converter follow the same current reference from the master converter, all these converters will be generating the same output current. That's how we realize the current sharing among the parallel power converters. These interactions through the current reference communications is really complicated the interactions of all parallel power converters. Wang Hao said, okay, can we model these interactions through the communication wire? Also, in terms of the impedance, let's see how the equivalent impedance of this converter is changed under the current sharing control. He figured out that, and he proved actually theoretically and by also simulation experimental verification, he proved that in this case, under master slave current sharing control, the equivalent impedance of this converter, no matter it is a master converter or slave converter, can both be obtained through 2 times of measurement. Okay, originally we just measure one time for each converter when there is no communications, no current sharing control between converters. When there is master slave current sharing control, we can measure, we can obtain the equivalent impedance changing by measuring each converter 2 times. Okay, let's say for the slave converter, we measure 1 time is when this current sharing control is invalid. Okay, we can tie the the input of the current sharing reference to high level to the float value point. Therefore, the current sharing reference signal and current sharing control is actually not valid. Okay, and you measure the impedance of the slave converter under this situation. And then the other time is that when you short circuit the current reference signal, so therefore the control circuit for current sharing is also is valid in this time, but the in this case there's no communication signal coming from the master module. And then under this case, you measure the output impedance, measure the impedance of the converter for another time. And he proved that the equivalent impedance of the converter under the normal current sharing control can be represented by this equation. Okay, the impedance, output impedance can be represented by this equation. That means it is, I mean, the master converter output impedance and slave converter impedance in these two situations. The situation with star is the output impedance when current sharing bus is connected to the DC source. That means it's when the current reference is short circuit, and the other output impedance of the slave module that we start without this star symbol is the output impedance we measured under the situation when the current sharing reference is current sharing part of this master slave of this slave converter is not valid. Okay, by combining these two times measured output impedance, we are able to get the equivalent output impedance of the slave module. This proved to be true not only for the master slave current sharing method, for every current sharing method, it is also true. Okay, that solved the problem. So under the case when there is communication, for example, the current sharing communication among different power converters, you can also obtain the equivalent impedance of the converter just by measuring each converter two times. Okay, there is a I don't have time going into the experimental verification of this conclusion. So therefore, even there is communications interactions among different power converters, for example, the current sharing communications, we are also able to handle it. The only difference is that in this case, all these converters under current sharing control has to be measured two times, okay? And then based on the multiple converter system stability checking criteria, we are able to check the overall system stability. For three-phase AC bus DPS, all these previously discussed stability checking criteria can be also adopted, but there's a difference. It's gonna be much more complicated because in this case, the power converter terminal characteristics, no matter when you are talking about the impedance or admittance, no matter which type, you always have at least 4 impedances for or 4 admittances, because even you are talking about the 2-channel, either in DQ channels or off-bit channels or positive sequence or negative sequence channels, you always have okay, these 2 channels, and therefore you always have a matrix of impedances of 2 by 2. Okay, so in this case, the Nyquist criteria is also extended to generalized Nyquist criteria. So when you have 2 3-phase AC bus connected converters, and their terminal impedances of a Z-type converter will be represented by this 2 by 2 impedance matrix. The terminal characteristics of a Y-type 3-phase AC converter can be represented by these 2 by 2 admittances. And then the generalized Nyquist criteria says the product of the impedance matrix of Z-type converter with the admittance of the 2 by 2 matrix of the admittance of this Y-type 3-phase AC converter, and these 2 matrices multiplied together can be used to check the overall stability. And in this case, because it is the product of this matrix is still a 2 by 2 matrix. So in this case, we need to treat this 2 by 2 matrix, which is called return ratio. Okay, this is called return ratio matrix. We'll check this return ratio matrix to check the stability. And because it is now matrix, adopting the generalized stability criteria, it means we have to look at the trajectory of the eigenvalue of this return ratio matrix and see for how many times these eigenvalues are whether eigenvalues of these eigenvalues are circling the -1,0 point, or for how many times these eigenvalues are circling the -1,0 point. Okay, by looking at that, we can check whether the system would be stable or not. That's what the generalized Nyquist criterion says. Okay, but then you can see there's issues. I mean, the physical interpretation is very obvious. Okay, but then because we're dealing with Nyquist criteria, we're dealing with these eigenvalues, and you have many eigenvalues. So it's not like in a single input and single output system when you have only one impedance or one product of impedances to check the stability, where you have when you can introduce stability margin concept. In this case, we don't have stability margin concept. That's one case, one issue there. On the another issue that is too complicated, you have two matrix. You have a matrix of impedance, you have a matrix of admittance. You multiply them together, you still have a matrix, and then you have to calculate the eigenvalue of this return ratio matrix, and then you check the for how many times they're circling the -1,0 point. That's very complicated. So therefore, there are issues there for three-phase AC system. One thing we have done in the last few years that we first was able to extend the idea of dealing with power converters when there is interactions through communications. The idea that we have proposed for DC bus system actually can be extended to a three-phase AC bus system. Okay, by measuring power converters 2 times, we are able to do that, and that was published in a paper also a few years ago by Dr. Liu Zeng. I don't have time getting the detail. The second idea that I was trying to introduce is that for actually checking the multiple three-phase AC power converter system stability, we don't actually have to utilize matrix even for the 2-channel system in DQ frame, alpha beta frame, or even in the positive sequence or negative sequence frame. We have 2 methods to simplify that. One method is to simplify the criteria. Okay, there was one criteria we proposed to simplify the criteria. We don't have to calculate the matrix eigenvalues. We can check just the very simply the infinity norm of the impedance. Okay, by checking that, we are able to check the system stability. Of course, that is a simplified criteria, therefore it's going to be conservative. But comparing to all the existing simplification, and here is a list of existing simplification criteria, our proposed simplified criteria is the most much less than the other proposed criteria conservativeness. Okay, it's simplified, also less conservative and other simplified criteria. The other approach we propose to simplify is that to use the complex coefficient transfer function. We prove that for symmetrical system, if both the power stage and control circuit are symmetrical, we prove that for a symmetrical system, checking the 2x2 return ratio matrix using generalized Nyquist criteria is equivalent to check the one-dimensional one-dimensional loop gain, one-dimensional complex coefficient transfer function loop gain or minor loop gain of the system. These two are actually equivalent. We proved that just a few years ago, and also in that sense, we don't have to treat this 2x2 matrix, return ratio matrix. We just look at the one-dimensional minor loop gain of this complex coefficient transfer function. We are able to check the stability, and therefore we can introduce the relative stability, like stability phase margin and gain margin concept. I don't have time to get into more details here. That's just the basic idea. And for more details, you can just check the paper for more details. One last thing I just mentioned a few, we already run out of time. I want to mention is that when you have in the DQ frame, especially in the DQ frame controlled power AC, three-phase AC power converters, we also noticed the thing which is actually not noticed by people before, was that the in the DQ frame there is also a what we call the dynamics of this DQ frame itself. Okay, and before we never notice, we never pay attention to the dynamics, the changing of the DQ frame itself. But actually the DQ frame itself has a dynamics. Okay, that dynamics will be affecting the stability of the three-phase AC power converter when it is connecting with other power converters. There was the initial concept was proposed also by Dr. Liu Zeng a few years ago, and this was also adopted later on by one of my PhD student, Wang Shike. He just last year she published this paper to using this concept of the dynamics of the DQ frame, the reference frame, or what we call as fundamental frequency dynamics, to look at the interactions, small signal interactions among group controlled inverters in the microgrid. Okay, and she was able to develop a set of small signal models considering both the traditional small signal dynamics and also the dynamics of the fundamental frequency, or the dynamics of the rotating frame. And she was able to develop a stability checking criteria to tackle the issues of the situation when you have multiple group controlled inverters connected together in the microgrid. Before, when we don't care, when if we do not consider the DQ frame dynamics or fundamental frequency dynamics, we were not able to explain. In many cases, there is a low frequency oscillation in the microgrid. Looks like we should be stable, even if we use the traditional impedance approach. I mean, no matter in three-phase or in the DQ frame, or in a single phase, or in complex coefficient transfer functions, but cannot explain with those traditional approach. Only when you consider that dynamics in a fundamental frequency and adopt the criteria that Wang Shike has proposed, we are able to explain those low frequency instability phenomena. For future work, I propose some work over here just for your reference. I think the case studies of the applications of impedance-based approach to stability analysis of practical DPS system should be considered. We need to really adopt the approach that I have mentioned, that I have introduced today, to all the typical practical cases. And we need to also have further investigations on the modeling process to make it more user-friendly. I have mentioned, no matter what I have talked about today, as at single converter level, for higher bandwidth modeling, or when we're dealing with the coupling among with three phases, these are so far quite complicated. We need to have user-friendly to make sure this process is simple and directive, and for DPS system is scalable. Okay, there are also more issues we have to look into, including how do we handle the asymmetrical three-phase system in a simple way. Okay, we have proposed several methods to deal with symmetrical system, but for asymmetrical system, how do we do it in a simple way? How to handle the transmission line impedances when the transmission network is very complicated and the transmission line impedance cannot be neglected. Okay, there are also issues that we have to consider beyond modeling. Okay, in the future, how we can model the system stability by doing some stability margin monitoring. Okay, online monitoring the stability margin. Okay, how can we reshape and redesign the converter impedances to make sure the whole system is stable? And how do we divine, come up with bus stabilizer? When the whole system is not stable, can we have just one single stabilizer, put it in the system to make sure the whole system is stable? How do we do the impedance measurement? How do we develop standards for all the power converters to follow when we are trying to connect this power converter to the system, to make sure in the beginning, once we connect our converter to the system, the whole system can still be guaranteed to be stable. So we need to develop standards on the impedances of power converters. So I'm sorry, I don't have time for question answers for the third part. If you have any questions regarding my lecture today, I will be very welcoming you through emails. You can send me your questions through emails later on. And again, also my lecture notes will be put available by the PD school organizers later on. And today's lecture video can be playback and using the web links you received later on through email.
So, okay, and Professor Liu, and thanks a lot for your very instructive lectures, and also appreciate your kind support to the whole PT school in this year. And so everyone, and thank you for all the attendance, and please notice that in the afternoon at 2 p.m. and we have the last lectures and of this PT school. And in addition, and tomorrow morning on 8:30, we have the International Forum on the electrolyzed and future energy systems. Also, and Professor Jinjun Liu and other experts from the worldwide will join the forum and have the discussions for the future in power systems with power tonics. Okay, so thank you, Professor Liu. Thank you, all the attendees. So I think if you have more questions, you can reach out to Professor Liu by email. Okay.
Yes, we will also see each other tomorrow. I will be
okay.
I'll be on the seminar tomorrow.
Okay, sure. And
thank you.
Thank you, and see you tomorrow, this afternoon and tomorrow. Okay.